A hockey team is practicing on a rink with an imaginary x and y coordinate system in units of meters. A puck is sitting at coordinates 6, 4 when player A passes it across the ice to player B. The puck moves at a constant velocity of 16 meters per second, assuming no friction, at an angle of 72 degrees relative to the x-axis. What are the coordinates of player B if they receive the puck in 2 seconds? So what's happening in this problem? We're working with coordinates, a velocity vector, and there's time involved. We have a hockey puck that starts at some initial position, then it moves with a constant velocity vector for a period of time, and ends up at a final position. Let's read through this again, draw a picture, and write down the important information. A hockey team is practicing on a rink with an imaginary x and y coordinate system in units of meters. So the problem is talking about a real-world scenario, but we're going to describe things as if they're happening on an x and y coordinate system. Let's draw the x and y axes to start the picture. Next, a puck is sitting at coordinates 6, 4. Let's draw a dot to represent the puck and label its coordinates. Since the coordinates are in meters, we can write down that the initial x position is 6 meters, and the initial y position is 4 meters. Player A passes it across the ice to player B. The puck moves at a constant velocity of 16 meters per second at an angle of 72 degrees relative to the x-axis. So let's draw the velocity vector of the puck and write down the magnitude, v, is 16 meters per second, and the angle, theta, is 72 degrees. The problem is asking us to find the coordinates of player B who receives the puck in 2 seconds. So the problem is basically saying if the puck has this initial position, then moves at this velocity, what's the position of the puck after 2 seconds? So let's draw a second dot for the final position of the puck, where player B is, and write down that we're trying to find its coordinates, x final and y final. Since we're working with vectors, we need the usual equations to find the components, or the magnitude and angle. But since this problem involves velocity, time, and initial and final positions, let's write down these two equations for displacement and velocity. They both use x, but we know the equations are the same for the y direction. We know the initial positions, the velocity, and the time, so we can find the displacements and the final positions. So before we dive in, let's talk through how we could solve this. One way is to use the velocity to find the displacement vector of the puck during those 2 seconds, and then find the x and y displacements, which we can add to the puck's initial positions to find the final positions. Another way is to find the x and y velocity components and use those to find the x and y displacements, and then add those to the initial positions. Let's try both ways to see what they look like. First, let's find the displacement vector and then find the components of the displacement. The puck is moving 16 meters per second in a straight line at 72 degrees. So after 2 seconds, the puck will move some distance in that same direction. So the displacement vector will have the same angle as the velocity vector. But what's the magnitude of the displacement? Since we're only looking at the motion in a straight line, we can treat it as a linear motion problem. Velocity equals the displacement divided by the period of time. Instead of delta x, let's use d for the magnitude of the displacement in the direction it's moving. So v equals d divided by time. We can rearrange that to isolate d on the left, and then plug in 16 meters per second for v and 2 seconds for delta t. That gives us 32 meters for the displacement. That's pretty simple math. The puck moves 16 meters per second for 2 seconds, so it travels 32 meters in that direction. Now that we have d, we can find the x and y components, how far the puck moved in the x and y directions. Using the trig functions, delta x equals d times the cosine of theta, and delta y equals d times the sine of theta. We plug in 32 meters for d and 72 degrees for theta. That gives us 9.9 meters for delta x and 30.4 meters for delta y. Now we can find the final positions of the puck. Delta x and delta y equal the final positions minus the initial positions. We can rearrange those to isolate the final positions, which means we're just adding the initial position plus the displacement. We plug in 6 meters for x initial and 9.9 meters for delta x to get 15.9 meters for x final. Then we can plug in 4 meters for y initial and 30.4 meters for delta y to get 34.4 meters for y final. Putting those together as coordinates, the final position of the puck would be 15.9, 34.4. Now let's look at the other way to solve this problem. First, we'll find the x and y velocity components. Then we'll use those to find delta x and delta y. So the x component, Vx, would be v times the cosine of theta, and Vy is v times the sine of theta. We plug in 16 meters per second for v and 72 degrees for theta, and we get 4.94 meters per second for Vx and 15.22 meters per second for Vy. So as the puck moves from the initial point to the final point, it moves to the right at 4.94 meters per second and moves up at 15.22 meters per second. Now we can use those to find delta x and delta y. We could use these two equations and solve this in 2 steps, but if we take the equation for velocity and replace delta x with x final minus x initial, and then we rearrange things, we get this equation, and we can calculate the final positions in 1 step. We plug in 6 meters for x initial, 4.94 meters per second for Vx, and 2 seconds for t. That gives us 15.9 meters for x final. For the y position, we plug in 4 meters for y initial, 15.22 meters per second for Vy, and 2 seconds for t. That gives us 34.4 meters for y final. That's the same answer we got before. We just did the steps in a different order. So that's an example of a problem that combines coordinates, vectors, and some kinematic equations.